Hello, welcome back students. My name is Dolon Banerjee and we are continuing with the geotechnical engineering video lectures. So now we will be talking about some important concepts and terminologies. Okay, so these you will be using a number of times during the whole lectures. So let us first of all go through these. So basic terms, just we will be describing some basic terms and their concepts and physical meanings. Okay, so let us move one by one. First of all, see into this graph. If you remember, I have already talked about this sieve analysis, okay, or particle distribution curve. We have already seen them in details. Okay, we also know how these curves are formed and how the cumulative are found out. Okay, cumulative percentages are found out, then how the curve is made. Okay, you know already that particle size distribution curve. Okay, so but you have to see that always we don't get a smooth curve. Okay, in field the soil may be gap graded or well graded or anything like that. Now what are these gap graded, well graded? We will look into this diagram so that you can have a picture of this. First of all, see this is a coarse grained soil. You can see it's written here coarse grained. Okay, it's a coarse grained soil like this. It is moving. This is coarse grain. This is a fine grained soil. Okay, just these are found out how these are differentiated just by the particle size. Okay, by the particle size from here to here it is made as fine grain. Why it is told as fine grain? Because you can see the maximum part is going inside this part. So this is called fine grain. And here why it is coarse grain? Because its maximum part, you can see this whole part is in coarser part or coarser region. So this is the coarse grain and this is the fine grain. Okay, first thing is this. Then now once you have seen these two, now you can see there are a number of diagrams in or lines made here. This is written as gap grade, this is well grade. Now what are these? This is uniform. Actually what happens, if you have a soil which has nearly every kind of particle, okay, if you have a soil whose you can say gradation or whose composition is in such a way that it is containing different types of particle from we can say fine grains to coarse grains, a number of different types of grains are mixed in that soil. So in that case what will happen, you will get a smooth curve and it will prolong from here to there. Why? Because it has fine grains also, it has coarse grain also. Okay, due to this it will be having a long curve here. You can see this curve, this one, this curve here, this curve here. You can see where has it started and where it has ended. So it has carried within it a lot of different types of grains in it of different sizes. Okay, so you can see its D10 is something like this, D30 is something like this. Okay, D60 is something like this. Variety, you can see this is 0.004 and this is 0.08. So you can see the variety of the particles in this soil. So this is called well graded. Why well graded? Because well graded. Why well graded? Because it contains a very wide variety of different sized particles. Okay, so this is your well graded. Okay, this is your well graded. Now let us talk about gap graded. What is gap graded? This one, this curve here is called gap graded. you can see it is also a very long curve. It is starting from here and going up to here, but why it is not called as well graded? Because you can see this part here, it is flat. Okay, it is flat. It is flat. What does this mean? That here in this region it does not have any soil particles of this size from here to here, which means what? It has particles here, it has particles here, but it has no particles here, means there is a gap in particle size in this region. So, it is called as gap graded. Okay, do you understand this? The gap graded, just you can say that gap graded. Region of size for particles is missing. Okay, so this is the gap graded. Now, I think you have understood this is the gapping. Then let us move to the final one, which is your uniform soil. This is your uniform soil. One second. This is your uniform soil. Okay, this is your uniform soil. Now, why is it called as uniform? Because you can see the range is very low. Most of the particles you can see in this region, in this part you can see that most of the particles lie here only, means most of the particles are near about this of same size. Near about of same size means that it is uniform, means most of the size of the particles in that soil which constitutes that soil is actually of same size or nearly of same size. So, this part here you can see how steep the curve is. So, due to this only it is called uniform, because same size particles are dominant in this soil. Okay. So, uniform same sized particle is dominant, or a range of particle is highest constituent of these soils. Okay. Sorry. So, this is it, you can see, you can note it down. Okay. So, now you are clear with what is fine grain, what is gap graded, what is uniform, what is well graded and coarse grain. Okay. Okay. You can also draw this diagram in rough, so that you can understand what are these. Okay. So, now let us move forward. Corrections to hydrometer analysis. If you remember what was hydrometer analysis, we actually carried out the hydrometer analysis in order to hydrometer analysis. Why was this carried out? If you remember, this was carried out to grade or classify fine grained soil. Fine grained soil. Okay. So, there I also had told you about the meniscus correction. Okay, if you can recollect that. Beside that, actually in this analysis we have three main corrections. One is the meniscus correction, one is temperature correction and dispersing agent correction. Okay, CM, CT, CD. Now, what are these? Actually, meniscus correction, if you remember, I have told you, suppose this is the cylinder, okay, measuring cylinder, something like this. Now you have filled the water in. The water will have a surface like this, okay, due to its cohesive property, you know. So once you have filled it and the soil is put into it and mixed thoroughly, what will happen? The water will get turbid, okay. This water will get turbid. I'm sorry. This will get turbid, okay. Turbid means low visibility. So what will happen when you see the reading? Try to see the reading. This is your eye, suppose. When you see the reading, you have to see actually this one, but you, due to turbidity, you see this one. You see this one instead of this one. You see this one, okay. So what will happen due to this? You have a erroneous reading, okay. This much error you constitute in your reading, okay. So what you have to do? You actually have to take this reading. You have taken this reading. So a positive correction is to be applied in order to get to this part, okay. On this is the meniscus reading. Since the suspension is opaque, the reading will be taken at the top of the meniscus, while the actual reading should be taken at the bottom of the meniscus. As I told you, it is constant for hydrometer and always positive, okay. Now temperature correction. What is temperature correction? Actually, these analyses or these experiments are carried out at 27 degrees centigrade. This is the standard condition for temperature, but there can be different condition, and it may not be that you are always constituting your experiment at 27 degree exactly. So it may be higher than that or lower than that. So in that case, you have to provide the temperature correction. So you can see if the temperature T is less than 27 degree centigrade, then it will have a negative correction, and if the temperature is greater than 27 degree centigrade, then you have to apply the positive correction, okay. You can see here also that is temperature less than, then the correction will be negative, and vice versa, okay. Temperature should be measured from starting till end of the test at regular intervals and are averaged. Then it is compared with the standard temperature, that is 27 degrees centigrade. So this was another concept. And what is dispersing agent correction? Dispersing agent correction, you know that yesterday I told you about flocculation. Flocculation. What happens? This flocculation, in order to remove this flocculation, because once flocculation is caused, the hydrometer analysis will be not properly carried out. Or why? Because once they have made the flocks in the water, their descending time will alter, their properties will alter. So your test or your analysis will be not valid, it will not remain valid at all from that point of time. So what we have to ensure that each of the particle is discrete, okay, their settlement is discrete, so that they can follow the Stokes law, okay. So once we have to remove this flocculation, what we did yesterday, if you remember, we added a Calgon solution, or what is this? What is Calgon solution? This was a deflocculator, okay, deflocculator, also named as sodium hexametaphosphate, okay, this is sodium hexametaphosphate. So obviously when we will add some chemical into the water, even though its region may be the deflocculation, but what will happen? It will increase the specific gravity and density of the water, which was actually to be, okay, it will be increased. So due to this, what will happen? You can see the specific gravity gets increased, okay, it will all increase. So due to this, the correction will be always negative, because we have to reduce the specific gravity. So the correction will be always negative in this case, okay. So these were the three corrections which we consider in the hydrometer analysis. Now what is plasticity index? Let us see. Plasticity index represented by IP. range of consistency or water content within which the soil behaves as plastic material is called plasticity index. How is this range found out? It is generally WL minus WP. This is plastic limit, this is liquid limit. These two, the difference of these two will give you the region in which the soil will remain plastic, that is your plasticity index. Plasticity index is expressed in percentage of the dry weight of the soil. In general, plasticity index depends only on the amount of clay present. Okay. It indicates the fineness of the soil and capacity of the soil to change shape without altering the volume. High plasticity index indicates that excess of clay is there. Why? Because in the previous class, if you remember, I told you that the plasticity and plastic properties are actually only talked about fine grained. Okay. And what is the fine grained? Fine grained is clay. So, if the soil is having a high plasticity or has a very high plasticity index, this means it has a very high range in which the soil will remain plastic. Okay. It will have a high range in which the soil will remain plastic. The soil will remain plastic. This means what? That there is a high content of clay, because clay is the only one particle which causes the plasticity. So, if there is a high plasticity index, it means that the clay content of that soil is high. Okay. So, the same is written here. Now, there are some values you can see. From this also you can understand. See, this is for sand and silt. You can see plasticity index, how less it is, 0 to 1. So, it is called non-plastic. If it is higher than 1 point, see if there are some traces of clay or little clay, accordingly they are getting increased. So, it will be low, slight plastic or low plastic. Then clay loam means it is high, because with loam it is clay also there. Okay. So, it is medium plastic. Then silty clay means now clay content is higher. So, again the plasticity, it is high plasticity, and if only clay we are talking, then you can see it is greater than 35, very high plasticity. Okay. So, these are the different cases of plasticity index. So, this was one of the index. Now, let us go to the next index, that is your consistency index. What is consistency index? Consistency, you know already what is consistency. According to that, it will be the consistency index, or the relative consistency, is defined as the ratio of liquid limit minus the natural water content to the plasticity index. Okay. This is L, plasticity limit. Okay. Ci you can write as WL minus WN upon, this is N, upon WL minus WP. What are these? This is liquid limit. Okay. These are liquid limit. This is water content in natural condition. So, I have written it N. This is your water content at natural condition. What is this? This is plastic limit. So, the difference will give you the consistency index. Okay. The ratio of these will be giving you the consistency index. Now, this consistency index helps us to know in what condition the soil is. Okay. Either the soil is in dry condition or wet condition or liquid condition, that we can find out from this consistency index only. Okay. So, let us see how is it done. Consistency index is useful in the study of field behavior of saturated fine grained soil. If consistency index of a soil is equal to unity, if it is 1, what does that mean? This means that this is equal to WP. Only in that condition then they will cancel out, giving you 1. What does that mean? That the soil in the natural state is at plastic limit. Okay. The soil in the natural state or in the ground is at the plastic limit. Okay. This is at plastic limit. Then a soil with equal to 0 is at liquid limit. Why at liquid limit? Because when it will be 0, WL minus WL upon IP. Okay. This is the formula. They get 0 when they are equal. They are equal means the soil at its natural condition is at liquid limit, means it is flowing like liquid or it is in liquid state. Okay. If it exceeds unity, the soil is in a semi solid state and will be stiff. When will it exceed unity? When will its value be greater than unity? Only then, only when the difference of this is less than the difference of this. Okay. What does this mean? Example, you can say, suppose the difference of these two numerators comes out to be 6, and this comes out to be 4. So, 1 point something. Okay. So, this gives you what? This gives you that it is greater than 1. Okay. It is greater than 1, which means you are having a semi-solid state of the soil. Negative consistency index indicates that the soil has a natural water content greater than the liquid limit and hence behaves just like a liquid. Okay. Means negative. What does this mean? Negative means the Ci will be water liquid limit minus something here which is Wn. This is greater than Wl. So, only in that condition it can be negative. Okay. Only in that condition it can be negative, because Ip is a different parameter. We are only fluctuating, or we can only vary this part. So, to make it negative, this must be greater than Wl, which means again the soil is in the liquid condition. Okay, the soil is in liquid condition. I think you have understood this. Okay. So, this part helps us to identify in which condition or which state the soil is using the consistency index. Okay. So, let us move forward. Liquidity index. This is also nearly same to the consistency index, but you can see the formula is different. Okay. Now, in this case what will happen? Liquidity index Wn minus Wp upon Wl minus Wp. You can see the difference in the formula. This is liquid limit, this is plastic limit, this is plastic limit, and now here it is the natural water content. Okay, in this place. The liquidity index or water plasticity ratio is the ratio expressed as percentage of the natural water content of a soil minus its plastic limit to its plasticity index. This is what I have written here. Okay. Again, in this also we can find out the state of the soil. How? If this is less than 0, if liquidity index is less than 0, how can this be less than 0? Means it is negative, means this part is less than this, okay, or this is greater, means it will be in the dry or brittle state. Okay. Something, if you remember the graph, Wl, Wp, Ws, the natural water content must be in this part only then this will be bigger. So, it will be in dry and brittle condition. If it is in between 0 to 1, then the soil is in the plastic state. 0 to 1 means if it is, let us suppose, half. What does that mean? If it is half, what does that mean? It is lying in this area. Okay. So, this is it is telling us. If greater than 1, then the liquid. Obviously, if it is greater than 1, because this is already the difference between them. Okay. If it is greater than 1, this means that this is greater than Wl. So, it will be somewhere here. So, it will be liquid. The soil will be behaving as a liquid. Okay. So, let us move forward. Toughness index. What is toughness index? The ratio of plasticity index and flow index of the soil. It is the toughness index. You can see this is the formula. This gives us an idea of shear strength of the soil at plastic limit. When toughness index is less than 1, the soil is said to be friable, okay, friable, which means it can be easily crushed at plastic limit, means with our hand also we can crush it. Okay. The toughness index is a very good parameter to check whether the soil can resist a load or not. Okay. Can resist a given load or not. Generally, you can see the value for clay soil it is 0 to 3, and for soils which are friable at plastic limit it will be less than 1. Okay, this is your toughness index, ratio of plasticity index to flow index. Shrinkage index, this is just like as you have just seen, this is just the difference between liquid and shrinkage limit. Okay, liquid limit and shrinkage limit. What was plasticity index? Plasticity index was Wl minus Wp, if you remember. Okay, Ip plasticity index was, and what will be shrinkage limit? You can write it like this, Wl minus Ws. Okay, just this is the difference. Now, we have different ranges for this as well. For 20 less than 20, it is swelling property. Okay, for this it is also showing your the different swelling properties. this is a very important parameter. Why? Swelling property, because shrinkage index is telling us about the swelling, and I already told you that if a soil swells much, then the formation of building on it is a very risky proposal. So, once we check out the swelling property or swelling potential of any soil, only after that we go on making a building. Okay. So, in other way we can say that shrinkage index is to be checked there. Okay. Activity of soil. What is activity of soil? Activity of soil actually is AC, represented by AC. It is your IP upon percentage clay. You can see the ratio of plasticity index to the percentage of clay size, where C is the percentage of clay size of particle less than 0.002 mm. Okay. Activity is derived conveniently from slope of a straight line as well. A steeper slope means greater activity. Now, this is your formula, the first thing. Second thing, you can see clay mineral, which clay mineral it is containing. This clay, which clay, this clay, which mineral it is made up of. Either it is kaolinite, okay, or it may be elite, okay, or it may be montmorillonite, somewhere this, either this or elite. Okay, only these three particles are the main which cause the soil to expand or gives the clay or expansive property. Okay, this is what we measured by this activity. We actually see how much the swelling potential of or expansive soil, okay, there is, how much the swelling potential is there. We actually check this. If there is montmorillonite, then it will be high activity or high swelling property, because it is very smaller in size. Okay, it is because it is small. Okay, this is relatively bigger, not bigger, but relatively bigger in comparison to montmorillonite. Okay. So, if it is if this clay is containing kaolinite, it will be having low activity, but if it is made of montmorillonite, it will be having a very high activity. Okay. Hence, swelling potential will be also high. This is your general classification. 0.75 means inactive, 1.125 normal, and greater than this it is active. Okay. It is the severe case. Then unconfined compressive strength, okay, represented by QU. It is an experiment to find out how the strength, what is the strength of the soil to resist the pressure or load onto it. Something like this, a soil specimen is made and load is applied to it. How much this soil or pat resists this load is what we will be finding out in this unconfined compressive strength. It is getting compressed. So, compressive strength. And why unconfined? Because we are not confining this. Okay, we are not confining this. So, it is the unconfined. Okay. So, the unconfined compressive strength is defined as the ultimate load per unit area, cross sectional area, that a standard cylindrical specimen of soil can take under compression without any lateral pressure, no lateral pressure, only compression. Okay. We will be doing this later on, just to give you a glimpse. Now, what happens? There are 2 to 3 things which you have to now understand. What happens is, when a soil is in the ground, okay, it is inside the ground somewhere here, then it is showing a different property or different shear strength. But once you dig it, this part you dig it, you remove, and you remove this part as well out. Okay. Now, this soil is here. Due to the remolding of this soil, okay, because it was here, it was in a different form, in a dense form, and many other things. Due to remolding, what happens? It loses its shear strength. Okay. So, we will be talking about this phenomena. Cohesive soil upon remolding lose a part of shear strength. The loss of strength of clay soils from remolding is caused primarily by the destruction of clay particles structure that was developed during the original process of sedimentation, and also disturbance due to water molecules in adsorbed layer. Main loss of shear strength is due to two reasons. Okay, the first is that due to the remolding. Okay, remolding. Okay, and the second is the destruction of the clay particles structure. The first reason is this and the second reason is this. Okay, these are the two reasons. Now see what will this cause. From this we arise with a sensation named as sensitivity of soil. Sensitivity is the measure of loss of shear strength with remolding. ST is defined as the ratio of unconfined compressive strength of the clay in undisturbed state, okay, to unconfined compressive strength of the same clay in remolded state, means ST remolded. Okay, as to QU undisturbed upon QU remolded. This is your formula. Now you have understood what is this. Okay, what there will be the shear strength loss. Okay, in a remolded part it will be the shear strength loss. So generally the sensitivity is greater than 1 only. You can see different classification. Less than 1 insensitive, 1 to 2 slightly sensitive, 2 to 4 medium, 4 to 8 very sensitive, 16 slight quick. Quick means this is now what does this quick means? Quick means the thing which is a quicksand condition. Okay, quicksand condition we will come upon later on. Then 16 to 32 medium quick, 32 to 64 very quick, greater than 64 extra quick. Okay, so this is the general concept of sensitivity of the soil. It just tells us how much the shear strength loss has been occurred due to remolding of that soil. Okay, now let us move forward. Thixotropy. What is thixotropy? The same phenomena which I just now talked about is sensitivity. In it you might remember that I told you that there is the loss of shear strength. There is the loss of shear strength upon remolding. You can see there is a loss of shear strength, but with time what will happen? Thixotropy is the process of softening caused by remolding, followed by a time dependent return to the original harder state. Okay, higher the sensitivity, larger will be the thixotropic hardening. Okay, minerals that absorb large quantity of water in lattice structures such as montmorillonite has greater thixotropic grain compared to other stable clay minerals. Mainly here what you have to understand is that with time after remolding, you know that the shear strength is lost, okay, due to two reasons I told you. One was permanent destruction and the second was due to remolding. This permanent destruction cannot be recovered, it is gone. Suppose if x part of it was due to x part of the shear strength was due to the structure, then this cannot be regained, but this remolding can be regained with time. Okay, this hardening means the regaining of the shear strength caused or lost due to the remolding only. Okay, due to remolding only. So this will slowly get up to a place, but it will never equal to this, because a part of it will always be lost which was the due to structure. Okay, structure, this will never be regained. So you understood that out of these two, remolding can be regained after this much shear strength can be regained, but due to structure the shear strength cannot be regained. So it will be like this, something like this you can say. If it was the initial, it will fall, then something like this. Again if you remold, again remold and continue remolding, then it will slowly reduce. Okay, this is your thixotropy. Okay, summing up, we can get some idea of sensitivity and thixotropy, plasticity and liquidity indices. Okay, so we will be continuing the further topics in the next class. Please continue watching the videos. Thank you.